All right. So let's go over some problems with quasi-quotation and unquote. So I'll fire up a Racket instance right now. So if I want to build a Racket list normally, I would do quote, and then open list 1, 2, 3, and then close with list with the close parentheses. And this satisfies list ha. It also satisfies cons ha, because all lists are con cells. Con cells are links that represent that you build linked lists out of con cells by chaining them together. All right, so far we've just seen this normal sort of 1, 2, 3 list. Let's also build up something like, say we did something like X, Y, Z, where we could use symbols instead. But let's say we wanted to do something like 1, 2, and then X, where X was some variable that we defined. So let's say we want to do something like define X to be 20. Then we want to do something like 1, 2, X. Well, if we do that in Racket, it's just going to force that last thing to be quoted. Because the way to understand that is when you see this tick and then this open thing right here with a few different elements, A0, A1, and A2, let's say. What that kind of translates into is list and then distributing that tick through the entire thing. A0, tick A1, tick A2. And we can see this by seeing that we have equal of tick X, Y, Z, and list, which is a function to create a list of tick X, tick Y, and tick Z. All right, so those two are equal, All right, but how would we do this example right here if we wanted to put in an X, where X was defined right here to be 20? Well, this is where we can use something called quasi-quotation, which is a slightly different form of quotation in Racket. Quotation is the process by which we build data rather than building code, which is the thing we're sort of normally doing, right? So quasi-quotation uses this backtick character rather than just the single uptick. And it works just like normal quotation. We can do 1, 2. That'll build the normal list 1, 2. But we can also do 1, 2, and then we can do what's called unquote. And we do that with a comma. So the idea is that we stick a comma before something, and then the idea is that Racket starts evaluating whatever this expression is, and then splices that into the entire list. So this is still telling us to build a list. It's telling us to build a list where the first thing is tick 1, because everything under this tick is implicitly kind of quoted now. So we've got tick 1, tick 2, and tick 1 and tick 2 just evaluate to the numbers 1 and 2. And then now we have unquote, this comma. And so that takes us from being in the quote mode of building data to now evaluating code, and then sort of putting that code, whatever that code ends up being evaluated to, end up putting that value right here in for X. So if we do that, Racket is going to build the list of 1, 2, and then 20, where 20 is taking the place of X. All right. So let's do this with some more examples. We can define L to be, let's say, 1, 2, 3. We can define X to be 10, define Z to be the string hello. And now we can build lists like, for example, L, X, Z, with each of those unquoted. And that's a list of 3 things. The first thing is the list, 1, 2, 3. The second thing is the number 10. And the third thing is the string hello. All right, and notice that even though this L is a list right here, it's only sort of putting it in as a sub-list. It's not lifting up these elements from that list 1, 2, 3 into the list as a whole. It's sticking this as sort of a subcomponent. So the first element of this big outer list that we produced is this sort of inner list of 1, 2, 3 for L right here. All right, so now let's do something like, so there is also a way you can avoid this behavior. So let's say you want to do tick X, tick Z, and then you want 1, 2, 3 to be the last few characters. Well, then you can use what's called unquote splicing. What unquote splicing does is it assumes that the thing here to the right evaluates to a list. So it will assume that L evaluates to a list, and it will then append that list into whatever position this is. And you can actually do it multiple times. So I can do at L here, and this should give me 1, 2, 3, 1, 2, 3. So I've kind of copied the list just by using unquote splicing. So just to say it again, the unquote right here would normally pull up L as a sublist, so it would normally do this. But if you wanted to pull up each of these individual lists out here and make them part of the outer list, you need to do this unquote splicing thing, which will have the effect of lifting that list and then splicing it into the list as a whole. That's why it's called unquote splicing. Okay, and I guess the next thing I should say is that you can do things like build up nested data. So I can build up something like tree, node, tick, plus 2, 3, node, tick, plus 4, 5, and this is tree of node 3, node 5, 9. So the way this works is that we start building up the data right here. So we've got this backtick. Then the first element of this outer list is tree, which is a symbol. The second is this inner list, the first element of which is the symbol node. And then the second element of which splices in that value plus 2, 3. So it evaluates 2 plus 3, and then it sticks that value in right here. And then over here we've got plus 4, 5. And then 9 gets put in right here because plus 4, 5 evaluates to 9. And this is a very common way in which we build up structured data in Racket. All right? Okay. So just like we can quote and unquote data, we can also match over it. So I'm going to build out matching right now. So I'm going to match something like tree, node, 12, node, 15. So this is the expression we're matching. Let's say we just want to get the 12 and the 15 and add them together. Well, then we could do something like tree, node, tick, or unquote x, and then node, and then unquote y. We could get both of them, and we could do plus x, y. All right, so let's run that, make sure it works, and it does. All right, and the reason it works is because match is going to match up. This is a quasi-quote. This is what's called a quasi-pattern. So this thing right here is going to it's trying to match up this with this, except these little unquotes that are going to be in the quasi-pattern are then going to be sort of filled in with the values of 12 and 15 when it matches. All right, we could also add some other cases here. So let's say we change the structure of this data so that we could have a tree with only a single node. All right, then we could do something like build up another match statement. This first one won't match, but we could also have something like tree, node, x. And in this case, we might just return x. Right? And in this case, the first one wouldn't match because tree right here matches, and then node, and then x matches right here, but then there's another element where there isn't right here. But then in the second one, we get the match. So if we run this, we should get the answer 12. All right? And then we could also imagine writing something like this. That wouldn't match any of the clauses. So to do that, we could add a default case. Usually we just don't want to add a default case though, because match failures really do represent places where the program is fundamentally broken. So whether to let match failures kind of happen or try to detect them and handle them gracefully is kind of a stylistic decision that we probably don't have the right context to answer, at least for a program, this kind of cartoonishly small. But if we had a larger program, we would want to be thoughtful about how we wanted to handle cases where the data didn't match and try to think about whether that actually signaled whether there's something wrong with our code or whether we needed to sort of rethink about how to do some kind of error handling or something like that. Okay, And then I guess another thing that we could encounter is that we have something like, let's say node hello. Well, now we're going to get this problem here where we've matched node y against this string, and so y is going to be taken in for the value of hello, but we really only wanted it to be a number. And so we could enforce that actually by doing question mark number, and then y. And that's going to change this quasi-pattern so that it only matches when this number predicate is satisfied, and then it will bind this variable y. All right. So now we're just going to see that there's no matching clause. And if we change it back to something like 12, then we'll see there is again. All right. Okay, great. So I guess the next exercise I'm going to cover is how to write something like MergeSort or some sorting algorithm in Racket. And this is one I actually haven't thought too much about. So it'll be interesting to kind of develop it from scratch. So I have a version of the imperative MergeSort algorithm right here. So MergeSort of some array takes some, I think, index into the array, and then some other index into the array. I think that's what it is. So let's see if we can read it. We say if r is greater than L, find the middle point to divide the arrays in halves, call MergeSort on the first half, and call MergeSort on the second half, and then merge the two halves together sorted in step 2 and 3. Okay, so I think this is kind of a crummy, crummy way to specify the algorithm because it's actually a little bit obfuscated. And I think if we rewrite this functionally, it'll actually become even clearer what's going to happen. So let's just dive into it. We want to define a function that's going to take some list and it's going to split it in half. I'm going to write a function called listSplitL, because that's clearly one of the things that we kind of need to be able to do. We need to take lists and we need to be able to divide them into smaller and smaller chunks until we get down to atomic chunks at which we can then reassemble those different pieces. So this is an instance of something called divide and conquer, where you basically take the input, you break it down into something smaller and smaller, and then you rebuild it up back over the back the other way when you're kind of going in the other direction. All right, so first we can split the list. So how do we split the list in half? Well, let's say that I've got a list like 1, 2, 3, 4. I want the answer to be 1, 2, and then 3, 4. Right, so I want these two different values back. So the first thing that I have to know is that I'm going to return multiple different values from this function. All right, and that's a very critical thing, is that observing that list split actually needs to retain or return two different values. And how can we return two different values? Well, there are a few ways to do it. I'm going to teach you sort of the one that you're probably most prepared to understand right now, and is actually the way that it works under the hood. So if we need to return a pair of something, we can always just use a consel. Consels are Racket's primitive representations of pairs. So like if I wanted to return the pair of the list 1, 2 and the list 3, 4, well, I could just cons up 1, 2, and 3, 4. And I actually want you to observe something funny about this. It's kind of interesting that here we see that when Racket prints this out, it prints this out as 1, 2, and 3, 4. You might have been thinking that it would look something more like this. But the key is to remember that actually, because this cons expression doesn't sort of, what we're sort of doing here is we really want to be thinking about something like that, right? So if I did that, I can see if I put this dot right here, which signifies that there's a consel here. This is sort of an improper list, if you remember when we talked about improper lists in class. Improper lists are things that are list-like, but don't have the empty list as their last element. Well, the observation is that really this, the cons of 1, 2, and 3, 4, is literally the same as a list where the first element is the sublist 1, 2, and the third element is 3, and then the fourth element is 4. And if you are sort of having more trouble visualizing that, I think that a good way to understand it would be to try to draw what this would look like in terms of the cons diagram. And then if you are still trying to trouble over it, feel free to let me know and we can work through it in person. All right, so first we have to return multiple values via cons. And then the next thing is that I need to know the length of the list. And that's because if I have 1, 2, 3, 4, well, I want to return 1, 2, and then 3, 4. So let's say that I know that the length of the list is, so let's define L or N as length of L. Now, I actually kind of like to build up my functions iteratively by interacting with them and having them return kind of the wrong result at first. So I'm going to do list split. This is sort of the way that I like to write my code, I guess, is to kind of rapidly interact with it by sort of running some of it in Dr. Racket and then running some of it over in the editor. And this sort of allows me the ability to kind of figure out how I can pull code from the REPL to then building it into my function. So let's think about what I would do with now that I've got this number n, which is the length of the list. I need to think, well, how would I get like half of the list? Well, the first thing is I need to know what half the list is, and I can call round for that, or sorry, I can call divide for that. But an issue if I have something like 5 divided by 2 is that actually Racket will return 2.5 for this answer. So in cases where I've got a list with an odd number of elements, I can't really divide it in half perfectly. I always have to kind of prefer one side or the other. So I think what I'm going to do is I'm actually going to do something like truncate in those scenarios. All right? So I'm going to say in define half length to be truncate in divided by 2. And now I need to write a function that's going to take 2 elements of this list and then return them for me. All right, so let's say I define a function that says, and this function is going to be called take. It's going to be L and then I. And there's actually a pretty nice tail recursive implementation of it that I could write, where I also define an initial accumulator. And I'm going to say if I is equal to 0, then just return the accumulator. Otherwise, return take of cdr of L, and then cons of car of L to ACC. So I'm going to extend the accumulator by 1, and then I'm going to take that cdr of 1, and then I'm going to return that. So now let's define first half as take L half length, and then the initial accumulator is going to be 0. And now let's just print that out. I need now I minus 1. I forgot that. All right. So I got the first half of the list, but I kind of messed it up a little bit. And this is actually a pretty common thing that happens when you write things in this tail recursive style. You end up reversing things. So I could call that function reverse to get me out of that bind. Or I could just write it in a not tail recursive style, right? I could just write it in direct style. And it kind of depends on what my applications are what my applications are for it. You know, maybe if it needs to run on really small numbers, it's not such a big deal to write it in a direct fashion. And actually writing in a direct fashion really in Racket should actually be fine. In some programming languages like OCaml that have more restricted stacks, this could be an issue, but actually Racket is pretty good at allowing you to handle direct recursion. So whether or not you use tail recursion is kind of up to you, although I would actually recommend it maybe a little bit less. Certainly not going to all the links to obfuscate your code to have to do it. So you don't always need to use tail recursion. There are definitely going to be some cases when tail recursion is actually quite tricky, for sure. And that kind of corresponds to the cases where you really do want to use recursion rather than loops. All right, so, but it turns out we're actually at a place here where if we add an answer, we can actually be pretty close. So now, I want you to observe, by the time we're in this I equals 0 condition, L is going to have the first 1, 2 having been pulled off of it and moved to ACC, and now L will contain the list 3, 4, 5. All right, we can actually see that if we do a begin block, which allows us to sequence statements. I haven't introduced that before, but begin just allows you to see a few different statements in a row, and it will execute them in sequence. And then I can do a display ln format here, a l, and then return reverse ACC. So if I do list split and then 1, 2, 3, 4, 5, I can see right when I return this accumulator, I actually have the rest of the list right here as well. And so I actually don't need to do anything other than just call take, because take is actually going to also be able to return 3, 4, 5. So I can actually just, instead of even returning reverse ACC, I can make this a cons of reverse ACC and L, and then this can be the answer to the entire problem. So if I do that, what I want to do is I want to make it so that the call to take is actually the return point of the function. So what I'm going to do is I'm going to have take, which I actually probably want to rename to loop, because now it's not just taking, it's also returning a whole bunch of the, returning the excess list. And now I have myself a nice little tail recursive implementation of a loop that splits it up. All right, see, so this is exactly what I want. And this is equivalent to so this is a cons cell where the first element of the cons cell is the list 1, 2, and the second element of the cons cell is 3, 4, 5. This is just how Racket displays cons cells. And then this is a list where the first element is the list 1, 2, and then the second element is 3, third element is 4, and fourth element is 5. So these are indistinguishable. In fact, they are the same thing, like we talked about earlier. So this is giving me the right answer. This is splitting the list in half. All right. So now I need to think about how I can build things into MergeSort. So let's define MergeSort of L. So the first thing I need is I need my different pieces in two different halves. So the first thing I have to do is I have to split the list. So I have to define first and second, which are going to be the first and second halves, to be list split of L. So now let's just display that, return that as the value. Okay, so now I get 1, 2, and then 3, 4, 5. So what I'm saying here is that I can just call list split right here, and then this is going to be first, second is then going to be a cons cell, right? In fact, I can convince myself of that by calling MergeSort and seeing that the result is in fact a cons cell, which is expected because that's exactly what we had just said with list split. But I'm just pointing that out again. So then how do we get access to the first half of the list and the second half? Well, we have a few options. First, we could do first half being car of first, second. Then we could do second half to be cooter, first, second. And then I could display each of these. All right. But instead of doing that, I could also just match on it directly. So I could match list split L cons first, second. And then I can write just the rest of my code for the function right here. So that's what I'm going to do instead, actually, just because it avoids typing extra stuff and a call to car and cooter, which I think you can sort of more systematically doing that using a match statement. All right, so now I need to call MergeSort. Sorry, I need to call sort. So the first thing I need to observe is that if length of L is equal to 1, then I just return L. So this is the base case. If the list is of length 1, just return L. The inductive case, if the list is of length greater than 1, split list into 2, call MergeSort on both sublists, merge each sublist back together. Okay, so now I've split the list into 2. I'm going to define sorted first to be MergeSort of L. And then I can do sorted second to be MergeSort of second, not L, first. And now I need a function merge, which merges them. Okay. And in fact, I would not have written the code this way. I would just have written this. Because I don't really like extraneous defines. Okay, so now let's define this function merge. I think probably we want it as an internal define because it's not going to be used by things outside of MergeSort. So let's do merge L0 and L1. And this is actually another nice recursive function. We want to take a function, this function merge. It's going to take 2 lists, both of which are sorted and only differ in length by 1 at most, and it's going to combine them. So it's going to take something like, let's say 0, 5, 6, and 1, 2, 7. So they're both like relatively sorted for each other, and then it's going to put them together. So it's going to pull, it's going to produce tick of 0 first, and then 1, and then 2, pulling from the second, and then 5, and then 6, and then 7. So this is actually a pretty nice little tail recursive function as well. I'm going to have, my template is going to look like, so let's match. So let's see, how am I going to do this? What I want to do is I want to pull off of either this one or this one, depending on which is smaller. So I always need to look at the first 2 of these lists, and then I'll take whichever one is smaller and put them in the accumulator. And then when both of them are empty, I just want to return the accumulator. But because of the same thing I mentioned earlier, the way that I'm going to do this is I'm actually going to keep consing onto the accumulator, so I'll actually be accumulating backwards. All right, so I'm going to just match L0, L1. There are a few different cases. The first case is when they're both, I can match of cons, L0, L1, and I can match cons of empty, empty. So notice that I'm matching after consing them here. So the first case is that they're both empty, and this is because I've got a cons of empty list and empty list. In this case, I just want to return the accumulator reversed. Otherwise, I have two different cases. I'm going to have cons of, let's say I've got a, let's see, I'm worried this is going to turn into something ugly, but I think it kind of doesn't have to be. So I'm going to do a head.head0.tail0 with head1 of tail1. Well, okay, I think I want to do the cases where the first one is empty, the other one is non-empty, I guess. This is L. If this is the case, then I want to reverse, I want to take everything in L and stick it onto the accumulator. So this is actually a little bit tricky because L is relatively sorted. I just want to add all of those things to the accumulator. So I want to basically reverse ACC and then append that to L, or prepend that to L, because this is everything so far built up in reverse order, and then L has the rest of the sorted things in this list right here. So this would be something like, L would be like, equals something like 5, 6, and then ACC would be something like 3, 2, 1, and then the result would be 1, 2, 3 from this reverse ACC, followed by 5, 6 by appending with L right there. So this is the behavior I want. And this is the case when I've exhausted everything in L0, but I've still got some stuff in L1. Otherwise, the analogous case, or the symmetric case, this is the same. I'm just going to copy and paste this code here. I'm sure I could make a little helper function or something if I wanted, but I don't really want to. And then this is the last and more general case. And in this case, we're going to say if head 0 is greater than head 1. Well, now I want to add the smaller thing to the accumulator, I believe. So I want to do merge of L0, and I would now want to choose and take head 1 off and then leave tail 1 to do that. So I'm going to do tail 1 right here, and then I'm going to do cons of head 1 on the accumulator right here. I'm going to say otherwise, I'm going to have the other option where I'm going to do L0, and then I'm going to want tail 0, and then cons of head 0, and then ACC. And I believe this also works if they're equal, because if they're equal, I think I can probably pull off of either list and it will be fine. Okay. So this was actually a pretty tricky function. Let's make sure that it actually works by running some tests on it ourselves. So let's write merge here. Let's do merge of 0, 1, and then 2, 3, and then see this. Oh, and it runs forever, so that's not good. So we messed something up. Okay, so definitely we messed up one of these. So we're going to do merge of here. Yeah, this shouldn't be L0. This should be TL0 and L1. Yeah, that's right, because it's this, we took the entire L0 unchanged, and now we're pulling off the head of list 1 and just getting its tail back. Here we had tail of L0, and then we have the rest of L1. All right, so that's what we made a mistake there. Let's go and see if we got it better now that we try again. So let's try this one test case, see what we get. Okay, so that one works. What about 0, 5, 1, 2, where it's going to have to splice them in? Oh, nice. 0, 1, 2, 5. Okay. What about 0, 1, 0, 1? Okay, so that works too. So I think that covers most of our cases. Certainly there's more testing we would want to do. Maybe we'll try to get the corner cases. 0, 1. Even though this wouldn't happen actually due to the way that MergeSort is going to be written. They're only going to differ by at most 1. But just maybe trying to be protective about it, I suppose. Oops. There we go. Okay, great. So it looks like merge works. So now, given that merge should work, and given that MergeSort should work here, I think MergeSort should basically work now. Let's see what we got. MergeSort. I don't know why I'm pronouncing it so strangely. 1, 2, 3. Ooh, that's not good. Oh, but remember, we wrote it in this tail recursive style. In fact, this is actually probably kind of a stupid way to do it. Probably we want to do define loop L0, L1, ACC. I'm going to reverse that one. That example doesn't make sense to anyone but me. Ah, shoot, went too far. Okay, now we're going to do loop of L0, L1, empty list. All right, let's see if we've gotten real luck this time. MergeSort 0, 1, 2, 3. Ooh, that's not good. That's very bad, isn't it? So now we just have to start debugging and figuring out what we've got. So I guess the most obvious thing is to just print out all the different places where we got called to MergeSort, just to initially see what's happening. So let's do MergeSort of 0, 1, 2, 3, and then we'll just see whether MergeSort was called with the correct different places. So this is I'm trying to debug the code. I don't know what's wrong with it, but we're going to fix it. So the first thing we need to know is, how is MergeSort being called? Okay, so it is actually being called on each of the sublists. So that implies to me that there's a problem with merge. So let's find out. So let's display let's do first MergeSort of first display ln. And then let's do second, merge sort of second, and then second, merge sort of second. And now let's do this again. Ah, this should have been format. My mistake. So this format function takes a format string and then the right number of arguments for it. Merge sort. Okay. Okay, here's the problem. So we're only ever returning this one thing. Okay. So second, merge sort of second. So now we need to consider this case where we've got two different things. Well, let's do list split of 2, 3. I see. Yeah, I'm not sure what's going on. Let's see. So we're calling merge with both of these things. So the call to merge, maybe let's print out okay, so we see merge 2, 3. Okay, first, merge sort of first. Yeah, I see. First, and then merge sort of first. Okay, so let's think carefully about what's going to happen if I just do merge sort of 0, 1. I just get 1. Okay. So now let's just think through what the code is going to do. So I've got merge sort of 0, 1. It's not going to hit this case. It's going to hit this case. So now I do list split of 0, 1. And I get what I expected. And now I see first is the list 0. Merge sort of first is the list 0. Second is the list 1. Merge sort of the list second is 1. That's all right. And then we get merge of merge sort first and then merge sort second. So now let's do merge of 0. Ah, shoot. Maybe I should have made it a top level define. Well, I'm going to stick to it. Let's see if merge is broken. Ooh, right. Needs that extra empty list as an argument. Oh, well, that's the problem. All right, so we just hadn't tested merge enough. All right, so I was just being silly when I wrote merge. Okay, so let's see what the problem is. So we've got merge L0, L1. Let's see, they're not both going to be empty. They're going to hit this case right here. And then we're going to see that we've got this case right here. Let's see, this case right here. So now I want to have head 1 when it's the smaller one. Otherwise, I want to do, so here I see, let's just print out display ln head 0, display ln head 1, display ln TL0, and display ln TL1. All right. So we'll do that like this. We'll redefine merge right here. Merge 0, 1, empty list. All right, so now I have merge 0, 1. We're right there. Head 0 is greater than head 1. No, that's not true. So we're going to hit this case right here. So now we're going to call merge with, this means we, that's the issue. So this means we need this, this means we need L1 right here, right? Or we don't want to take, we actually want this to be L0. We want to leave this undisturbed. We want this to be TL0. No. What am I doing? So in this case, yeah, we do want to take 0. And then we want to cons this onto the accumulator. So I'm not sure why this didn't work actually. We've got head 0 is 0. That's the one we want. So this is TL0 and this is L0. So let's see, this looks right to me. We've got merge of L0 where L0 is the list 0. L1 is the list of 1. And now head 0 is 0. We want it to be right here. That looks right. And this accumulator, I see. Merge, huh? I see. Also, we need to print out the accumulator. So let's try that. Oops. Okay, so this is silly. Now we're at this point where the accumulator, huh. I see. So we must have hit one of these cases right here. Yeah, I'm not really seeing what would happen. I would think we would hit this case right here. We would append. So let's see. This is the case that should be firing. Oops. We'll take this right here. Merge. 0, 1. Oops. I keep doing that. Okay, so it does here, but at that point, we already know the accumulator is 0. So I don't see why reverse of ACC I was being silly. It's because I really wanted loop. Oh, wow. That was a very tricky bug, actually. It's because I was calling merge right here, which is then going to take that initial accumulator and then just give me totally the wrong thing. That was so silly. Okay, oh well. So let's try it now. Okay, so let's do merge 0, 1. Oops. Ugh. This will be the end of me. Boom. Okay, great. So now let's do MergeSort of 0, 1, 2, 3. Okay, that works. MergeSort of 0. No, let's do 1, 0, 3, 2. 1, 2, 0, 3. Okay, let's start randomly testing this and seeing if it's right. So let's do for I in range 0 to 5,000. We want to write a function that generates a random list. So let's define generate random list of length L. And this is going to be cons of random 0. Let's do 20. No, let's do 200,000. Why not? And generate random list of, let's make that I1. And then let's say if I is equal to 0, then just return empty list, otherwise return this, and this will be fine. It's not tail recursive, but who cares? It's just testing code. Random list of some length, so let's do 50. And then let's just print that out just to see that we're actually generating sensible lists. So we're going to do it in the range of 0 to 2 so that I don't blow up my screen. Okay, so it looks like I'm generating some random lists actually. Good. Okay, so now what I'm going to do is I'm going to make sure that if I use Racket sort, I get the same thing as if I use my merge sort. So let's do merge sort of, let's let bind this. So let's say let x is going to be, or let test input list, and then be merge sort input list sort input list less than. Let's try it. See what we get. Let's just look at our version of MergeSort, and oof, we need to take off all our stupid debugging instrumentation. So we're going to take out that. Actually, we should probably comment it out, because if it is buggy, we're going to need to know how to debug it later. Okay. And all this stuff slows down the code too. So, all right. Let's take this, take that, also print that out, and then let's rerun it. Oops. No, that's not what I want. Oof, the computer is being very slow. All right, I'm just going to kill this process. Stop, 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 please. Quit running on the machine. All right. At some point in the future, this will stop. Come on. I'm gonna have to like manually kill the process. Okay, there we go. What is happening? I don't think I'm generating anything. I think I've commented out everything that would have happened. Yeah, I'm not sure why this is happening. I think it's just because Racket is overwhelmed that I'm streaming this stuff, and so it's like hasn't loaded the stuff into its buffer again. All right, well, I'm sorry about that. Let's write this to disk maybe. Maybe that will solve the problem. Sinsky. Example.rkt. Boom. And see, Dr. Racket won't even load it right now. Oof. All right, well, yeah. Sorry that Dr. Racket sucks. Okay. Let's see. Yeah, I think it's just that it's using a whole bunch of memory. And streaming is also taking a lot of bandwidth on my device. So we can take this and just copy and paste it into a new window, ignoring Dr. Racket.